Okay, and present. Okay, wait. Okay. So today we will do exercise, some tutorial. So as I've uploaded before for week 2, for the last 2 weeks, week 2 and week 3, the first chapter and second chapter, okay, of for propulsion. Okay, the first one was the introduction to everyday engine. So I've introduced the different types of everyday engine, turbofan, turbojet, turboprop, a bit about turboprop, etc. Right? And then in the second chapter, I've introduced some parameters, namely performance parameters, okay, in order to evaluate, okay, to analyze the performance of each engine propulsion engine jet, okay. So today, basically we will do we will see some examples of exercises, tutorials, in order to evaluate, okay, the performance. So actually the objective of propulsion course is exactly to evaluate performance, okay, because propulsion relate with the engine. So we want to evaluate the engine, whether we have to design a better engine, optimize the engine or what. Okay, but here in your propulsion course, we are not going to optimize it, not yet. Maybe in your elective course in final year, there is another course they call air breathing engine. Okay, that is elective course. It's actually an advanced course. We can say advanced course to propulsion. Okay, so that is in your final year elective. So if you are interested in learning more about propulsion and the engine, you can take in 2 years or in 1 year and a half later on. You can choose elective air breathing engine because it relates a lot with propulsion. You already know the basic, and then you be in everyday engine, we try to optimize, to try to think what are the design that we can do to improve propulsion jet. Okay, but here in second year course of propulsion, we more into just solve, okay, calculate and analyze the performance. Okay, not yet design or optimizing. Okay, just know that what is the problem. Okay, how much the performance, the calculations, etc. Okay. Dia lagi nak masuk. Okay. Okay, so why I just call this title chapter 2, because actually the chapter 1 just introduction, so that you know what is the everyday engine and how is the process, etc. So chapter 2, there was I explained all the equations. So we will apply all the equation, especially the thrust force equation today. Okay, to calculate some of the performance parameters. Okay, so it's better if you look back at the slides, especially the second chapter, the last week's slides, all the formulas. Okay. Okay, so we'll start. There are 3 questions to do today. If we not finish, if we can't finish, you can just continue calculation by yourself. Okay, so the first one is easy. This is just direct. Okay, so the first example exercise. So please have your paper, okay, to do some calculation, not just listening. Okay, please, even though I can't see you, but I hope that you try to do it. Okay, in 3 weeks we will have test 1. Okay, inshallah. So the first one, air flows through a jet engine at the rate of 30 kilogram per second, and the fuel flow rate is 1 kilogram per second. Okay, the exhaust gas leaves the jet nozzle with a relative velocity of 610 meter per second. Pressure equilibrium exits over the exit plane. Calculate, okay, the velocity of the airplane if the thrust power is 1.12, or I can change it to 1.12 megawatt. Okay, mega is 10 power of 6. Okay, so 1.12 megawatt. Okay, So this is a kind of direct questions, just that you have to substitute all the values in the formula, but a bit of the reformulation, you have to change a bit the formula, but it's still easy, okay? But here, the question give you power instead of Newton force, right? In terms of force, Newton. So because normally we know that thrust is in terms of the unit for thrust is a force. Okay, the force that propel the engine to move. Okay. Thrust is a force. Okay, but here it is given to you instead power. Okay, so you as an engineer, even though if you haven't learned the propulsion, you must know how to convert from Newton to power. Watt. From Newton to watt. From Newton is a force. So from force to power, how do we convert the value? Okay, from force to power, from work to power, from energy is joule, from energy to Newton. You must know that, not just for propulsion but for other cause static or dynamic, fluid mechanics, etc. Right? That is the basic engineering that you have to know by now. Okay, so from thrust, the equation of thrust force. Okay, I have introduced to you the equation of thrust force last week, right? The equation of thrust force. So from the Newton, here is given power watt. So what do we need in there? Okay, and how to solve this one? Solve this question to compute the velocity. Okay, please try to relate the equation of the thrust force in Newton with the value given in watt here. And all the parameters that we have here, airflow through a jet engine at the rate of 30 kilogram per second, means that it is 30 kilogram is the air mass flow rate, MA, air mass flow rate, and the fuel flow rate is the MF, okay, fuel, 1 kilogram. So look here, as I've mentioned in my class, the last two class, the fuel flow rate, the mass flow rate of the fuel is normally generally very, very small compared to the air mass flow rate, the total air mass flow rate that the air intake that goes into the engine. Okay, so that's why sometimes, you know, to simplify the equation of the thrust force, we assume that the mass flow rate is very small so that it is negligible. Okay, it's not that it is zero, it's not that it is have no value, but it is very small compared to the air mass flow rate. Okay, but here since it is given, even though it is small compared to air mass flow rate, it is given, so you have to take into consideration in your calculation because it is given, so you just take into consideration. Okay, even though the effect is not that big. Okay, and then the exhaust gas leave the jet nozzle with a relative velocity of 610 meter per second. So this one is the exit velocity. Okay, exit velocity, which is written as a VE or UE. Okay, in the thrust force calculation. Okay, and then it is said here, pressure equilibrium exists over the exit plane. So we assume that the exit pressure PE is equals to the ambient pressure, P ambient. So PE equals to PA. So what happened to the thrust force equation? Okay, it will be simplified, more simplified. Okay, so that's why I say it is easy. Okay, so try to do this one. Okay, later on I will ask some of you the answers or how you solve the problem. So I've already given some explanation, okay, on how to do it. Use the thrust force equation and try to relate that thrust force equation with the power. Okay, how to convert from force to power, from Newton to watt. What are the parameter that you need? What are the physical parameter that you need in order to convert force to power? Okay, any questions you want to ask? Okay, so I give you first the thrust force equation. I write this T. So the thrust force equation, the full one. Okay, I write the full one. M NA UE minus U. Okay. Okay. And plus, this is the general equation, PE minus PA. Right. PE minus PA. Okay. So, since it is said here that pressure equilibrium exits over the exit plane, okay. So, PE is equal to PA, okay, because the pressure is in equilibrium. So, we only have this term, okay, MA equals to UE minus U. Okay, here since this was the simplified thrust equation, so I want to rewrite it in terms of the real one, more the actual one, which we include the field mass flow rate, because field mass flow rate is given here. So instead of writing like this, okay, I write like this one, MA. Okay, this is definition first. So the thrust force is like a momentum, right? Momentum equation. So you have the mass flow rate at the exit times velocity at the exit minus mass flow rate at the inlet, which is the air mass flow rate, times the air speed U. So ME is actually, okay, from the conservation of mass, we know that mass is conserved. Okay, so ME at the exit is actually MA initially plus the MF fuel mass flow rate, right? At the exit, conservation of mass. So at the exit, the mass flow rate at the exit is actually the mass flow rate at the intake, which is MA, plus the fuel mass flow rate, MF. Okay, so UE minus, okay, this one. Okay, so this is actually the thrust force equation here. We cannot neglect the MF here because it is given 1 kilogram per second. So we write it like this. Okay. So and then how? From this thrust force, because this is in Newton, thrust force in Newton, or kilogram per kilogram meter per second square, right? So how do we convert this thrust force in Newton to thrust force in power? Because the value given here is in power, watt. So how do we convert that? What do we have to do? Do we have to multiply with something with value, or divide with another value, and what is the parameter? Okay, I'll ask someone. Nur Natasha Fitri.
Yes, doctor.
Okay, can you give me? I don't want the calculation yet. I'm just asking you, what do we have to do in order to convert from Newton to watt?
Force.
For the Newton is a force, and then what do we have to do? Because we have the value given here is in watt. So what do we have to multiply with something, divide to another value, or what? To change into what?
force multiply with velocity.
Okay, thank you. Thank you, Natasha. Okay, force multiply with velocity. Then we will have the force, which is the thrust in terms of power. What? Okay. So this value multiply with u, the velocity, u here, air velocity. So you have to u here and add u here and u square here. Multiply with u. So this is tu. Okay, thrust force u. Okay, so here we have the parameter u that we are going to search for. Okay, the question here, compute or calculate the velocity of the airplane, which is u, if the thrust power is 1.12 megawatt. Okay, so we know this is equals to 1.12 megawatt. Okay, so we know the value of MA, which is 30 just now. 30, right? Okay, 30. Fuel mass flow is 1. UE is 610. U, we don't know. We have to solve. MA is 30 again. So U square, we have to solve. Equals to 1.12. So it is a quadratic equation. Okay, power of 2. A linear equation of, not linear equation, sorry. Quadratic equation, which is a power of 2. So you have to solve this equation and get the value of U. You will have two values of U because it's a quadratic equation. So solve that. Later on, give me the answer for you. There are two answers of you. Possible answer of you. Means that there are two moments where the engine hit the power 1.12 megawatt. Ada yang tak ada ni. 24 tolak Yunus ada dulu. 22. Okay, just solve the quadratic equation. Calculate to solve U. Okay, I'll ask. Yunus, can you give me at least one answer for you? Velocity?
I'm not sure, doctor.
Are you calculating?
No, not yet.
What are you doing? Apa tengok buat? Tengah calculate ke tak?
Tengah tengok.
Tengah tengok.
Tak faham lah, doctor.
Trust force, tengok tak chapter last week? Tengok slides. Cuba buka slides. At the same time, try to open the slide, last week slide I think. Sebab ada equation. Last week slides, performance parameters. Dalam tu ada equation. So equation thrust force. This equation thrust ni memang yang paling penting. Lama-lama nanti memang kena ingat lah dalam kepala. Thrust force is the basic thrust lah. Basic yang lagi propulsion efficiency. Yeah, sorry, ada yang nak cakap ke? Okay, so I try to explain to the ones that maybe tak dapat catch up lagi. So daripada thrust force tu, because here we know the thrust power instead of force. The thrust force is in Newton. The general thrust equation is in Newton because it is a momentum equation. So like Newton's second law. Okay. So we have to change from thrust force to thrust power. So in order to change from Newton force to power, what? We have to multiply with velocity of the air. Okay. So thrust force multiplied with velocity, we will get thrust power. So here the question asks you to calculate the velocity. So since you know the thrust power, so you just add the thrust force equation, multiply with velocity. So you search for that velocity. Okay, it's like a quadratic equation. You have a quadratic equation, you square, and then solve the equation lah. Okay tak Yunus?
Boleh lah.
Faham juga lagi? Awak tengok tak slide tu ada tak? Download tak?
Ada. Tapi tak faham.
I think the first page ya. I accept the title lah. Anyone else? Any problem? Okay, Nakib bagi jawapan. Okay, 564.15 and 66.17 or 175. Okay, that is correct. Okay, I just want to make sure the others, do you understand or not? Because this is the like simple lah kan. Okay, so this at least you have to understand first this basic thrust equation first before we go proceed to second and third example. Okay tak? Apa yang tanya? Amira okay? Tadi nama Amira. Amira okay? Calculating ke tak? No je.
Doctor, I got different answers.
Okay, apa awak dapat?
Jawapan dia pelik doktor. Saya dapat 30.5 plus ni yang first. Saya dapat 30.5 plus 51.79 I. Tu kenapa?
Betul tak yang quadratic equation tu? Solve dia. Kan kena buat balik yang macam dulu-dulu belajar tu yang negative B plus minus square root B kuasa 2 tolak 4 AC over D.
Okay.
Benda-benda macam tu lah.
Okay.
Yeah. You have to use your knowledge for quadratic kan. Negative B plus minus square root B power of 2 minus 4 AC and then divide by 2A. Okay, then you will have two answers for you. Because we cannot factorize this equation directly kan. Or otherwise some of you now have advanced calculator. You can calculate, the calculator can solve directly quadratic equation. Okay, I proceed Saya proceed
Okay, Doctor.
Okay.
Yes, Doctor.
Okay, the second one, okay, you can see here. Second one, a turbofan engine is powering, so remember turbofan. So that's why we have cold and hot value. A turbofan engine is powering an aircraft flying at Mach number 0.9. Okay, Mach number 0.9 at an altitude of 33,000 feet. Where the ambient temperature and pressure are negative 50.4 degrees Celsius and 26.2 kilopascal. The engine bypass ratio is 3, and the hot airflow passing through the engine core is 22.7 kilogram per second. Preliminary analysis provided the following results. So we have F, okay, the ratio, the fuel mass fuel flow rate to mass air ratio F 0.015. So like I've said, since the value of the fuel mass flow rate normally look very small compared to the total air mass flow rate, so that's why the ratio F very small, okay, 0.015. And then we have the exit pressure for the cold and hot, okay. Cold and hot exit pressure. So just now this one is the ambient pressure. Okay, this is the exit pressure. So for turbojet, normally we have only one exit pressure, like just now. PE and PA, ambient. So for turbofan, since we have bypass duct, so we have like a two exit flow. Okay, so there is cold that we call cold and hot airflow. Okay, because there is the bypass duct, the cold airflow will exit through the bypass duct, and the hot airflow will exit through the core engine. The core engine is called the hot. Okay, the hot zone. The cold zone is the bypass. Okay, so PEC. Okay, kejap wait. Okay, sorry. Okay, continue. So PEC is the exit pressure, exhaust pressure from the cold engine, from the bypass duct. Okay, and PEH is the hot exit pressure from the core engine. Okay, means exit nozzle engine after the turbine and the nozzle. Okay, exhaust. Okay. Okay, but sometimes at turbofan engine there are two types of exit exhaust. There are mixed exhaust, or we call it separate exhaust. So here it is a separate exhaust because we have a different value for exit cold and hot. Okay, okay, so there are different types of turbofan engine for the exhaust. Okay. So and then UEC is the exit velocity from the bypass duct airflow, and UEH is from the core engine. And then the area, okay, the area is a little bit different, 0.299 and 0.229 meter square. So the area of the exit, okay, for the cold is 0.299, and from the hot, the area exit, the area exhaust nozzle is 0.229. Okay. Okay. Why we need the area? So actually the just now I forgot to add the area at the P. PE minus PA, right? You have to multiply with the area, even for turbojet. So I forgot that one just now, but it is negligible. It is the same just now, so the term is zero. But actually, you have to add the area because P times A is force. Okay, the pressure times area is force. The pressure, the pressure force. Okay. So here is given area for you because the exit pressure is not negligible, so you have to include. Okay. Now, so now that we have all these values, so calculate the thrust force. Okay, so what is the equation of thrust force for turbofan engine? So, okay, so normally for turbofan engine is a bit longer, the equation, the general equation of thrust force for turbofan engine, because it has two parts. One part is for cold and another part is for hot. Okay. So means that if for turbojet we only have two terms, the momentum thrust plus the pressure thrust, okay. But here for turbofan, it's like four terms, so it's you have to double, okay, double the equation, the thrust force equation, because you have one part for cold and one part for hot. Okay. I think is given in the equation for thrust for turbofan in the last week slide. Otherwise, you can try to derive the thrust force equation for turbofan by including another two terms, okay, for cold air. Faham tak apa saya cakap? Okay, equation thrust force untuk turbofan engine dia panjang sikit sebab dia ada dua parts. Dia ada parts hot and cold. Kalau turbojet dia ada satu je laluan dia. Okay, so tapi basically equation dia sama je. Basic dia sebab dia punya definition tu tetap sama, momentum and pressure force etc. So just that you have to exit flow, you have to add double lah the term. Kalau dia itu turbojet dia dua, dia ada tambah so dia ada 4 term. Tapi mass flow rate dia, pressure dia adalah perubahan sikit. Tapi definition tu sama. Okay. Okay, right here, but it's a bit longer. Thrust. So MH. So this is the core part. 1 plus F U E H minus U. Okay. And then plus M cold. U E C minus U. Okay. So this term first. So both of this term is the momentum thrust term. Okay. Just now for turbojet you only have this part, right? Okay. The hot air, the air mass flow that goes into the core engine for turbojet and for general equation thrust. Okay. So that is actually if you want to compare with the turbojet, the air mass flow that goes into the engine is the hot MH. And then this one, okay, we already factorized this here, okay. 1 plus F because of the conservation of mass, okay. Just now we have MA plus MF, right? The ME exit is equal to MA plus MF. Okay, so here MA is MH. Because MA, the total air intake is now separated into two, hot and cold. So this part is the hot part, okay, the hot section. Okay, so you have MH plus MH, the air mass flow that goes into the engine, the core engine, plus the fuel mass flow rate that that we put, okay. So but here since we know it is given in terms of fuel mass flow ratio, so we change the MF instead of putting here MF, so we reformulate it in terms of fuel ratio. So F fuel ratio, the definition MF over MA, right? So here for this one turbojet MA is actually MH, the hot air. So MF over MH. Okay. So since we know the term MH and F, and we don't know MF, so that's why we reformulate the MF in terms of F multiply MH. MH is factorized here. Okay. Okay. So this part is only the hot air from the core engine part, like the turbojet. Okay. Okay. So for turbofan, we have to add another term plus, okay, plus MC, the mass flow rate of the air that goes into the bypass duct. Okay. So we call it MC because M cold. It is colder than the F mass flow rate that goes into the engine. Okay, so MC is multiplied with UEC minus U. So the same definition of momentum thrust, M dot multiplied with U, velocity. But here, okay, we only have MC because we don't have fuel intake going into the bypass duct. The bypass duct is only air, no fuel. Okay, so only MC multiply with UEC, the exit U velocity from the coal bypass duct minus U the flight speed, the air speed. Okay, so this is only the momentum thrust, the momentum part. The pressure thrust, okay, so the pressure thrust, so plus, tak habis lagi okay, so plus, that's why it's longer than turbojet, plus, okay, if for turbofan, we have this equation, right? AE, A area, just now I forgot to add the area. AE, the pressure thrust, AE, multiply with PE, exit pressure, minus PA, ambient. Okay, PE minus PA. Okay, this is like the turbojet. Okay, but here for turbofan, we have to differentiate. This is H, the hot. Okay, the hot exit, plus the same thing for the cold part, PE, C minus PA. Okay, the same, exactly the same. Okay, just that this is H, this is C, because we have two flows or two airflow. Okay, so that's it. Okay, we have 4 terms for thrust equation for force. Okay, so once that we know all of this, so I think now we can derive, okay, calculate the thrust force. Okay, so we know is given a PEC, PEH, PEC, PEH, AEH, AEC. What else? UEC, UEH is given. F is given. MHMC. Okay, MHMC you have to calculate. Okay, from where? How do we know? Okay, MC is given the MH, and the hot airflow passing through the engine core is 22.7. So MH is 22.7. But how do we get MC? MH is 22.7. Okay, the hot airflow. So how do we get MC? The cold airflow, the air that goes into the bypass duct, MC.
Bypass ratio.
Yes, by using the bypass ratio. Okay, the definition of bypass ratio is what? Beta. We write it as beta, bypass ratio. So bypass ratio is MC over MH. Okay, MC over MH. So MH 22.7. This beta bypass is 3. So MH times 3. So we get MC. And what else do we need? There's another one that we have to calculate before we proceed the thrust force calculation. What else? Another one that we need to know. Apa lagi satu? Tak boleh nak calculate lagi thrust force ni, ada satu lagi yang tak ada, value.
Velocity of the
Yes, velocity. So how do we find the velocity? The U. How do we get the velocity? Look at the information given. What else that we haven't used yet?
Mach.
Mach number, okay? Mach number. So from the Mach number, you know the definition Mach number. So we can get U velocity. So we use Mach number multiply with the speed of sound. Speed of sound, you use the square root gamma RT. So gamma, okay. Normally for air in propulsion problems, we use the gamma for air 1.33, or you can still use 1.4. Just that the answer will be a bit different. Otherwise, please use 1.33. Okay, the gamma 1.33. R is 287. Saya lupa. 287 joule per kilogram per Kelvin. 287 for air now you have to know, okay, but normally I will give you this value parameter gamma 1.33 R 287 for speed of sound. Okay, so U equals to Mach number multiplied with speed of sound, which is square root gamma RT. T is ambient lah, ambient temperature, okay? Negative 50.4, so change into a Kelvin. So once you find U, then you can solve thrust force. And then try to calculate the propulsion efficiency as well. Okay. Sorry, hari ni saya kena sambil pegang baby. Because no one tak jaga dia. Okay.
Doctor,
Yeah.
the temperature, do we need to change to Kelvin? I think not right.
Untuk U kan?
Yes.
Kena lah saya. Kena. Sebab because R is in terms of 287.
Oh,
Joule per kilogram per Kelvin.
okay, Doctor. Thank you, Doctor.
So what you guys get for U, flight speed? U berapa?
2.432.
Tu apa? Tak dengar.
262.432.
262.
Betul ke?
Okay, acceptable. This the one that I have is 269, but it's okay. 262. I think because of the gamma. Okay. Okay, so 269 or 262 and then proceed for trust. Oh, saya dapat dah. Trust force just now. Okay, for trust force, you can just leave it in kilonewton, because if you just let the pressure in terms of kilopascal, so you don't need to convert to pascal. Okay, just let it be kilopascal, 26.2 pascal, kilopascal, and then you will have the answer in terms of kilonewton. Apa tu? 9,000 macam tak sangat. Kita dengar kawan-kawan dulu. Okay, thank you Zati. Ah, 4.4 tak juga. Oh, ada yang dah macam apa Zati Okay, sebab apa Ush, putar. Sekejap, ke saya kat mana yang tak sama betul? Sekejap. Because should be around 19 kilonewton. 19 point lah. Natasha dapat. Okay, 19.257 or around that I can accept lah. 2.57 kilonewton. 98.86 also can. Okay. Around 18 to 20 kilonewton I think is correct. Okay. Because of the velocity speed just now. So that might be some different in the calculation. But 9,000, 4,000 I think is different. Okay, it's wrong. I don't know. AMH is 22.7. 1 plus F. So 1.015. Okay, and then UEH 452. U is 269 or 262 just now. MC 68.1. Okay, MC 68.1. Okay. Okay, and the area is given. So I hope you try. I think the unit is already fine. Okay, unit is already fine. So the answer should be around 19 kilonewton. Okay. Okay, now the propulsive efficiency. Okay. Okay, propulsive efficiency. So I have written here the question for propulsive efficiency. This one. Okay. So okay, for turbojet, okay, the definition for propulsive efficiency is by definition, it is the thrust power divided by the thrust power plus the power wasted. Okay, so this is the total. This below is like the total, and above is the actual power that we produce, that the engine produce. So below is the total power inserted. Okay, so the definition is the same as in thermodynamic cycle, right? We have the energy or the total power inserted, and the above is the actual power produced or the actual energy produced. Okay, so that is the definition of propulsive efficiency. So here, in terms of power, we have the total power produced over the power produced, the thrust power produced plus the power wasted. Okay, the power loss, the energy loss. Okay, so here, so the energy loss or the power loss here in terms of power is defined as the kinetic energy or kinetic power loss. Okay, wasted. So this is like the kinetic energy equation, right? 1/2 mv square. Okay, the kinetic energy. So here power, so m dot u square. So the so the waste so this part is the same. This first term is the same as in turbojet. Okay, 1/2 m dot exit, the mass flow rate at the exit, hot, and u square. Since it is power wasted, so we have to define u exit minus u. So what we have to calculate what is the difference in terms of velocity. Okay, ue minus u, because we want to identify, quantify the power wasted here. So ue minus u square. So there is actually the velocity as if the velocity energy wasted. So that is for hot. Okay, hot, which is the same as in turbojet. Plus for turbofan, another momentum, kinetic energy, another kinetic power wasted in the bypass, in the core, in the cold air. So MC, right? So because in cold air we don't have difference between exit and inlet air. Kalau cold, yang inlet MH is different than MEH because we add the fuel. Here at the cold, bypass duct, the MC inlet is the same as MC outlet. So we just write MC. Okay, so MC again multiply with the energy wasted, the kinetic energy wasted, which is defined here as the difference in terms of velocity, UEC minus U square. Don't forget square. So, okay, remember like the kinetic energy equation 1/2 mv square. So V here is UE minus U square, okay? So power wasted. Okay, so for turbofan engine, the power wasted is the total power wasted in the hot air and the cold air. Okay, so 1/2 ni multiply dengan semua semua mv kuasa 2 ni. Okay, this is like the momentum kinetic equation multiply 1/2. So T we already know thrust force. Okay, sorry. Okay, thrust force multiply with U velocity. Okay, and the rest I think we already have the values, so we can compute the propulsive efficiency. Baru masuk ke Syairah? Assalamualaikum, Syairah baru masuk ke? Ke tadi terkeluar? Terkeluar dah balik. Propulsive efficiency, ya. So for turbojet, just until this part, okay? Okay ke? Okay? This is propulsive efficiency, ya, macam integral pula. Okay, propulsive efficiency. So for propulsion, the main performance parameters that we usually use is thrust, propulsive efficiency, thrust, propulsive efficiency. So that is the main performance parameters. There are others, okay, like I've mentioned in the slides, like specific impulse, specific thrust. Another one is TSFC, the thrust specific fuel consumption. There is another important parameters also for a jet engine. Thrust specific fuel consumption is a calculation of how much the mass flow rate, the fuel mass flow rate needed to produce 1 kilonewton of thrust, for example. In order to produce 1 Newton thrust, how much fuel is needed? Is more used in terms of to identify if you want to save fuel, okay, the usage of fuel. So we have to calculate how we have to know how much fuel is used for each type of propulsion engine takeoff, for example, cruising. Okay. But here we don't. Do I have example? Okay. So how much propulsion efficiency? Oh, for those yang tak dapat apa tu tadi thrust tu different, you have to take at least 19.257 or 19.864 thrust. Otherwise, your propulsion efficiency also will be different, right?
Doctor, is the answer 0.9?
Yes, 0.9, 90%.
Okay.
Okay, around 90%. If you use the thrust 19 kilonewton just now. Okay. So we get the answer around 90%. 90.32% or 0.9. Okay. We proceed. Okay, everyone. Try to finish your calculation later on, okay? Okay, next. Okay. Ada TSMC kat sini. Okay. Okay, so this is again turbofan engine. Because turbofan is more complicated than turbojet. Okay, so Boeing 747 aircraft is powered by CF6 turbofan engines. So these are the following data that we have for turbofan engine. So we have thrust force 24 kilonewton, air mass flow rate to 125, bypass ratio 5, fuel mass flow rate to 0.75, Mach number 0.8, etc. etc. Okay. So if the thrust generated from the fan, okay. So just now when we calculate all the thrust equation, the thrust force is actually the total thrust force. So when you have for turbofan, you have the term cold and hot, right? So actually the thrust produced is by the bypass or the fan and the core engine. So you have two separate thrust force produced. Okay, but the one that we calculate just now is the total. We already sum up both of the thrust force. Okay. So that's why the term is double. Okay, so here the thrust generated from the fan is 75% of the total thrust. Means from the total thrust that we have 24 kilonewton, 75% is produced by the fan, from the fan. Okay, and then okay, so we have to determine okay the jet velocities of the cold air and hot gas. Okay, cold air, the cold part and the hot. Okay, so the fan is actually from the cold, okay, from the bypass. Okay, and the specific thrust is thrust over mass flow rate of the air. Okay, T over MA. And the TSFC, MF over T, and the overall efficiency. Overall efficiency is a bit long, we see with that. So overall efficiency is actually propulsive efficiency multiplied with thermal efficiency. Okay, so normally in thermodynamic cycle, we calculate only the thermal efficiency, right? Thermal efficiency. But here in jet engine, we are more concerned, we are more interested in the propulsive efficiency. But sometimes you also calculate the overall efficiency. So overall is actually propulsive multiplied with thermal. Thermal efficiency for jet engine is mainly on the efficiency of the fuel, thermal fuel, because that is where the combustion process occur. So that is where the thermal power, thermal energy is produced. Okay. Okay, so this one, jet velocity of the cold air and hot gas. So by now you already know how to at least the basic one, the velocity thrust equation, you already know. Okay. Fan mass flow rate is given here. Fan mass flow rate or the cold mass flow rate. Fan mass flow rate or cold. Okay, just now we use the term cold mass flow rate. Here we use fan, so it's the same. So the fan mass flow rate is the one that goes into the bypass duct, the air flow that goes into bypass duct. So 104.2, and the core engine is 20 kilogram per second. Okay, the core engine or the hot air. Okay, so here we can see that normally the airflow, the air that goes into the bypass or the fan is a lot more higher than core. So 104.20 is, so the bypass is around 5. 120 ya. 100 bagi 5, 25 kan. So bypass ratio 5. So how to begin? To calculate the jet velocity, so means that we have to calculate UEH or UE here is core, okay? UE exit velocity of the core engine and the exit velocity of from the fan or the cold part. UEC, UEH just now. Okay, so or here we call it as UE fan or UE core. So you have to calculate UE for both. So what do we have here? We have the thrust force. We know the total thrust. And we know that 75% is from the fan and should be 25% from the core engine. And then what else do we have here? We have the air mass flow rate. So definitely we have to use that. And what else? U flight. Okay, U the air speed by using the Mach number. Okay, like just now we have here Mach number, so we can, and the ambient temperature, so we can calculate U, the air speed. So thrust UE, U mass flow rate ada UE. So you can from the thrust equation, from the separate thrust equation, we have thrust, we have mass flow rate, we have U from the Mach number, so we can derive UE for each fan and core. Faham tak? Okay. So you have, okay, pardon. Okay, P fan, I call here fan. So the thrust of the fan, 0.75 of the total thrust kan? Of the total thrust, so how much? 0.75 times 24 kilonewton, so we have 18 kilonewton. And for the core, thrust produced from the core engine is 0.25 total, so 6 kilonewton. Okay, so 24. The sum, the total will be 24 kilonewton. Okay, so since we know the separate thrust produced by both of the airflow, the flow, fan and core, so try to write the equation of thrust for separate fan and core. So just now, for second exercise, we have the equation of thrust force for the total. Okay, so just take the fan part and just take the core part and equals it to the thrust fan and thrust core. Okay, thrust fan you have M of the fan, or MC just now, this time is M of the fan, UE from the fan, minus U of the SP. Okay, this is the thrust equation for fan. Okay, so try to write the equation, the same thrust equation for core. It's from the total thrust equation just now. Just take the fan part and the core part, the core engine. Oh, I forgot to add here. Assume that the exit pressure. So the pressure thrust, we assume that it is negligible. So PE equals to PA, right? So no need to include the PE, PA part. Pressure thrust, only the momentum thrust. The momentum here. Okay, so to solve this, you need to calculate U first, flight speed. So like just now, U equals to Mach number times square root gamma RT, the ambient. So we got U, and M fan is 104.2, thrust fan 18 kilonewton. So you get UEF, the jet velocity from the coal or the fan. And the same to be done for core engine. So core engine, except that here you have to have the fuel 1 plus F. UEF 520. Different sikit. I have around 400. You, what do you get for you? You the flight speed? You?
Flight speed 348.
248.
Something like that.
I think 233 tu betul. 233 tu right, or 240 if you use 1.4. If you use 1.33 then you get to 233. Otherwise the rest is direct, right? So UEF should be around 400. Yang lain dapat berapa? The rest 200 sikit pula. Sikit pula. $406, okay. $406 acceptable. Okay, TFN is 18 kilonewton. MF is 104 just now. And then plus U here is 240 or 233. So we have UE, okay, around 400, 406, 413, something like that. Okay, and then next T-core. T-core, you have to add ME core here. Not E, M core here. So you sorry, 1 plus F UEC minus U. Okay, don't forget 1 plus F. For F, fuel, you have to do some calculation. M fuel is 0.75, right? 0.75 over the hot, only the hot, not the total air. Okay, the one, the core engine mass flow rate, okay, 20.8. So 0.75 over 20.8. So that is your F fuel ratio. Okay, because fuel ratio is the ratio of the fuel mass flow rate over the air that goes into the engine, core engine. So 0.75 over 20. So you get around 0.036 the fuel F ratio. Okay, so how much for UEC or UEH? Okay, 503. Okay, around that 503, 510. Okay, and then for the next B and C, okay, the specific trust and TSFC is direct. Just use the formula. Specific trust is trust over MA, the total trust over MA, and for the TSFC is the fuel mass flow rate MF over T, total trust. So that is direct. Okay. For overall efficiency, you need to calculate the propulsion efficiency using the formula just now, like exercise 2. And thermal efficiency. Okay, thermal efficiency I will give you. Okay, in the meantime, try to proceed calculation first. Okay, I will write the thermal efficiency equation. Okay, so for thermal efficiency, the definition is the ratio of the above is the power given to engine airflow. How much power we give to the engine airflow over this one is the rate of engine supply to the fuel, which is the rate of energy from the fuel. Okay, rate of energy of the fuel, m dot plus the fuel heating value. Fuel heating value is given here. Fuel heating value is like specific heat, CP, right? Specific heat for air, for example, you have 1005, right? So here for fuel jet engine, we use the value, the physical value, QR, which is fuel heating value, around 42 or 42.8 or sometimes 43 megajoule, or we write it as 42,800 kilojoule. Okay, so this is fuel heating value. So it is a characteristic of the fuel. So the fuel, each fuel, it has a heating value. Okay. like the specific heat, right? How much the energy joule we can produce for each kilogram for each joule per kilogram or for each temperature for one period of temperature. Okay, so this is fuel heating value. It's a parameter given. MF is the mass flow rate, fuel mass flow rate. So above is the power actually given to the airflow, okay, for it to propel, okay. So that is the thermal efficiency. So thermal efficiency linked with the fuel efficiency, fuel energy of the fuel. Okay, thermal lah. Okay, so for turbofan, okay, we have to add the extra part, okay, for the coal or the fan, okay. So the same, you have TU power plus the like kinetic energy just now, okay. Okay, so 1/2 MV, okay, the same as the propulsion efficiency just now, plus 1/2 M dot C, okay, MR. So this part is like the same as in the propulsive efficiency, except that the below we have MFQ. The above is the same as in propulsive efficiency calculation. Okay, so for question B and C, B specific thrust is 192. So directly just 24 divide with 125. The total air mass flow rate 125. So you have 192 meter per second. Or you can leave it in 0.192 kilonewton. Okay, I write it here. So the first one is a specific thrust. Okay. Second one, TSFC. So TSFC means that in order to produce 1 kilonewton of thrust, we need 0.03125 kilogram per second fuel. Okay, that is the definition. Okay, next for propulsive and thermal efficiency, and then overall efficiency. Okay, in order to calculate overall efficiency, you must calculate first propulsive efficiency and then thermal efficiency. Okay, and then propulsive multiply thermal and then you get overall. Okay, so 71 multiplied with 25 and then you get 17 or nearly 18%.
Doctor, what is TSFC again?
Just now, the answer or what? The answer is 0.031. I have written here.
Yeah, I mean the meaning of TSFC.
Okay. M is an F over thrust, right? So mean that in order to produce 1 kilonewton of thrust, how much fuel you need? How much fuel do you need in order to produce 1 kilonewton of thrust? So it's more to quantify to calculate the fuel that you need. Okay.
Oh, okay. All right. Thank you, Doctor.
Because normally if you want to design an engine to modify engine to get a better engine with a better fuel consumption, okay, better fuel saving, so obviously normally you have to compare to evaluate the TSFC with the conventional engine and the new design engine that you are going to propose. We compare the TSFC normally. Sorry, so this is the Google form for attendance, okay? So I finished the 3 example. You can continue the calculation. Okay, you can capture the answer values given here in the chat box and try to finish the calculation. Okay. And then you can fill in the attendance, and we finish. Okay, I stop recording.